Here's our third example. We have a student combining 50.0 milliliters of 2 molar potassium iodide solution, and it tells us we're mixing it with a very concentrated solution of lead 2 nitrate. So we have to, again, know what these formulas for these compounds are. We have lead 2 nitrate and potassium iodide. Of course, you should know what that is as well. And we're going to mix these two solutions together. So the very first thing that we should do, of course it asks us to do this, is to write our balanced chemical equation. So we have potassium iodide, and we have a potassium iodide solution, right? So that translates to aqueous. And we're mixing it with a lead 2 nitrate solution. Okay, so that's aqueous as well. All right. Now it tells us a precipitate forms. And we'll talk about this more in the coming days. But the precipitate that's going to form is going to be the result of these cations and anions switching partners. And this is what's called a double displacement reaction. You see, we start out with potassium and iodide together, and lead and nitrate together. But what's going to end up happening is the potassium is going to end up pairing with the nitrate, and the lead is going to go with the iodide. And so what we're going to end up with is lead, not lead 2 nitrate, but lead 2 iodide. And this is going to be our precipitate. Precipitate just means that we're going to form a solid, so we're going to mix these two solutions together, and as a result we're going to see a solid. And we're going to end up forming potassium nitrate as well. And potassium nitrate is not going to be a precipitate. It's going to end up being dissolved. Now, you'll also notice that I had to add this coefficient here to balance the reaction. And I'll have to add this here to balance the reaction as well. We have 2 iodides to go with these two here. We have 1 lead, okay, 2 nitrates, 2 potassiums. Everything should be balanced. And again, it's critical that you start out with a balanced chemical equation, otherwise you're going to be in trouble. Now it says, assuming that the lead 2 nitrate is present in excess, tell how many grams of precipitate are expected to form. So we are told that we have this solution here, it's present in excess, meaning we're going to form this precipitate, and we want to know how much we're going to get. But basically what they're saying is, don't worry about the amount of lead 2 nitrate that you have. You have all the lead 2 nitrate that you need. Our output here of the precipitate is going to be limited by the potassium iodide alone. So once again, we're going to take the 50 milliliters, convert that to liters, 0.050 liters, and we're going to have 2.00 moles of potassium iodide per liter. Okay. And then we're going to end up with 0.100 mole of potassium iodide. All right. Now, here's where we can look at our equation. We see that 2 moles of potassium iodide react with just 1 mole, or react to form 1 mole of lead 2 iodide. And so 0.100 moles of potassium iodide. 2 moles of this form 1 mole of the lead 2 iodide precipitate. And so now we're back to 0.050 moles. Okay. And this is of the lead 2 iodide. And we were asked to find the grams, so 0.050 moles of potassium iodide. And the molar mass there, I got about 461 grams per mole. And so when we solve this, finally we should get 23.1 grams Pb2 led to iodide. This is our theoretical yield, meaning in theory we should get this, but we may not if the reaction doesn't go according to plan, or if we're not able to completely isolate all the precipitate out, either by centrifuge or by filtration. We may not get the correct amount, okay? And so this is why it's called the theoretical yield as compared to the actual yield.